Now we're going to look at how to apply a variety of math techniques to prove that one expression is either the same or different from another expression. Here we're seeing a description of what it means to prove an identity. So it begins by looking like an equation. You'll have something on the left side equal to something on the right, but you'll only be working on one side of the identity. I'll be asking you guys to only work on the left-hand side just so I can control which operations and substitutions you're performing, but you're only going to be performing substitutions and simplifying steps and multiplying things out on that left-hand side, and you're working towards what you see on the other side, the right-hand side, to see if the two statements are equal or not. So the proof will begin with what you have on the left, the proof will end with what you see on the right-hand side, and your work will be showing a sequence of steps where it's very easy to identify what substitution you made or what kind of multiplication operation you've performed. You never want to try to do too many things at once so that it's easy to the reader to see exactly which math rule they have used to go from one line to the next. So these do need to be done in a very neat and orderly fashion. The way I work them out and what I encourage you guys to do is to write your steps down vertically so that I can see what's being substituted in what spot and what kind of rules you're using from line to line. So now that we've talked about what a proof looks like, what about which technique can you actually use to change your left side and make it match the right-hand side? And that's what I'm describing here. One of the most common strategies is changing the entire expression to one using only sines and cosines. So if you see a lot of tangents, cotangents, secants, or cosecants in the expression on the left-hand side, you may want to perform substitutions, replacing all of those with rules in terms of sines and cosines only. Make sure you change everything, otherwise you may not have some of the terms cancel out. Another useful thing to look for is whenever you have trig functions, especially trig functions being raised to the second power, specifically when they're raised to the second power, it doesn't work for other exponents. And if you see a 1 being added or subtracted from that, you might want to look at your list of Pythagorean identities to see if there's a substitution that can be performed there. Our factoring techniques are still very important for proofs. You always want to look for a GCF first, see if all the terms have anything in common that can be factored out. If there are two terms, you may want to see if it matches a difference of squares setup. Difference of squares is probably the most important one to know forwards and backwards because it'll also help us with multiplying out some of our products. If you know how to go from a squared minus b squared to a plus b, a minus b, or to go backwards from a plus b times a minus b into a squared minus b squared, it's very helpful. And also our trinomial factoring. So when you see three terms specifically, you have something like an x squared plus x plus a number. Your trinomial factoring may help break the polynomial into smaller parts, and then those parts may cancel in some future step. And the last strategy is for whenever you see some fractions, you will usually, instead of having two fractions being added or subtracted, want to get a common denominator between those two, and then you can combine those fractions into one. And then again, that sometimes causes something to factor out or cancel out in the following steps. So these are the techniques that you'll want to apply on the left-hand side of the formula, but never do too many of them at once. Always just try to do one thing at a time so that it's easy for a person to read what you've done from one step to the next. It's also a good idea to mention that there is no one way of proving the identities. Many times you'll find yourself in a step where you could actually apply multiple of these strategies. You might even be able to perform all four of them. So you'll want to kind of plan ahead and keep looking at what you have on the right-hand side of the equation to get a hint or some guidance on which step would be the best one to make next. But many times it actually doesn't matter which one you pick. All that changes is it may end up taking more or less steps than if you had picked a different technique. So when all else fails, if you find yourself getting kind of backed into a corner, you may want to look back at an earlier step you made and see if you could have made a different choice out of this list of strategies. And maybe that other choice would have been easier to finish solving from there. So here's our first example. You can see that I have on the left-hand side of the equal symbol, this is the statement I'm going to be working with. I want to manipulate tangent of x plus cotangent of x and keep doing substitutions and operations on it until it ends up looking like this right-hand side, secant of x, cosecant of x. So the first thing we want to do is look through the possible strategies we can apply and then pick which one we think is best for this particular problem. For this first step, I do see a lot of tangents, cotangents, secants, or cosecants. So this is an option to change everything to sines and cosines. I did not see trig functions being raised to the second power, so I don't see a Pythagorean identity I could use. I also don't see any factoring techniques that could be applied, so this one's not an option right now. And I didn't have any fractions that were being added or subtracted, so I don't see a way to combine fractions. So in this case, there's only one step that's open to me, and that's going to be to rewrite all of the trig expressions using sines and cosines only. So here you can see on the left-hand side of the equation, I have performed two different substitutions. I replaced tangent with sine over cosine, and I replaced cotangent with cosine over sine. So it is important to know the rules for what the different trig functions are equal to in terms of sines and cosines, but this is what I meant by saying change them to sines and cosines. And I, again, have only worked on the left-hand side. So by keeping things in a neat, organized fashion, you can tell that tangent was replaced with this and cotangent was replaced with this, so on the left and on the right. So now we need to perform another operations, because right now my left side and my right side do not match. You don't have to keep copying down the right-hand side as long as you just write in equals. Then we assume that nothing has changed on the other side, and that's our intention. We do not want to change anything over there. So you can just keep working on the left and writing equals, and then stop when you hit the information on the other side. So now let's go back to our list of strategies and see which one we can perform next. Well, we've just changed everything to sines and cosines, so we don't have any more expressions that we can rewrite using sine and cosine. Everything has already been done for that. So this one is not an option for our next step. The second option is Pythagorean identities. None of my trig functions are being raised to the second power, so we don't have any options for a Pythagorean identity for this step. I do not see any factoring either. There wasn't a GCF, there weren't any squares, nor was it a minus sign in between them to make it a difference of squares. And we only have two terms, so it can't be a trinomial either. So none of our factoring techniques can be applied. But I do have two fractions that are being added, so let's see what happens if we combine them by getting a common denominator. So remember that to get a common denominator, you need to take the denominator of each fraction and multiply it by the other fraction. So this denominator of sine of x needs to be multiplied on top and bottom. And the reason we're allowed to do this is because if I multiply by sine over sine, well, a number divided by itself is actually equal to 1. So this fraction will not be having its value changed, it'll only change what it looks like. Then I'm going to do the same thing the other way around. This fraction has a denominator of cosine, so I need to multiply that on the top and the bottom of the fraction on the right-hand side. So now that we've set up that the fraction on the left has a denominator of sine times cosine and the fraction on the right has a denominator of sine times cosine, we can combine these into one fraction that says sine of x times cosine of x. And then on top, we need to make sure we perform the operations. So sine times sine is sine squared. And cosine times cosine is cosine squared. So now we have combined these two fractions that were being added into one fraction over a common denominator. Now this still doesn't match what we have on the other side, so let's go back to our strategies. We still already have everything in terms of sine and cosine, so I can't use this option. I did see trig expressions to the second power, so we'll want to look at Pythagorean identities that can be applied. There isn't any factoring, and we've already done the combining fractions. So I haven't had many choices to make for this particular example. Sometimes you will have options, but for this one, I have to pick a Pythagorean identity. That was the only option that was available. There's an identity that says sine squared plus cosine squared equals 1. Since sine squared plus cosine squared equals 1, I went ahead and I replaced the numerator of our fraction with a 1. So now we have 1 over sine times cosine. We've almost finished this problem. We're getting really close. The last thing you might want to note is that sine and cosine are both the reciprocals of secants and cosecants. And this particular fraction could be written as two different fractions, one of them saying 1 over sine, and then multiplying that by 1 over cosine instead. So it's kind of like we're splitting this fraction up because 1 times 1 is still 1, sine times cosine is sine cosine. And then this makes it easier to recognize that the reciprocal of sine is cosecant, and the reciprocal of cosine is secant. And it practically matches what I have on the other side, but it is important to note as a step here that yes, we are allowed to change the order for two numbers being multiplied. 2 times 3 is the same as 3 times 2. So it is okay for me to replace the previous step, cosecant times secant, with secant times cosecant instead. So this is our proof. We've gone through and only working on the left-hand side, we've written a series of equivalent statements that will hopefully be easy to read and see what we've done from one line to the next. And we knew that we were done once we hit what was on the right-hand side of the equation. We were working towards secant times cosecant. And now that I have that, we have confirmed or proved that tangent of x plus cotangent is actually the same as secant times cosecant. Here's a second example, and I will go through this one a little bit faster now, but I do still want to show you a little bit of what happens when you have a choice on which strategy you use. So here we have 1 over secant of x minus 1 plus 1 over secant of x plus 1. We're only going to work with this information, and we're going to try and get it to equal 2 times cotangent times cosecant. Currently, the problem does have some expressions we could change to sines and cosines, so this one is potentially an option for us right now. However, I did not have any trig expressions to the second power, so there shouldn't be any Pythagorean identities to use. I did not see any factoring that could be done. However, there are also 2 fractions being added and subtracted. So this is a case where we actually have to make a choice. And if you look back at the problem, the advice I would give you is you want to try to avoid to make a choice that makes the problem more complicated. And since we would have fractions inside of fractions by replacing the secants with 1 over cosines, that would probably not be my first choice in the problem. So I would say that it's actually better for us to instead try to get a common denominator and write them as one fraction. So as I described, on this one I'm going to try to get a common denominator. So I went ahead and showed my setup that I'll be multiplying the left by secant of x plus 1 and the right by secant of x minus 1. So then I can just go ahead and compute these. Now I did put a lot of parentheses to make sure that we remember to actually distribute this out, secant of x plus 1 times secant of x minus 1. And since that is kind of our difference of squares factoring, if you have a plus b times a minus b, as a shortcut, you can recognize that this is secant squared of x minus 1. A squared minus b squared factors to be a plus b times a minus b. So it's like I used the difference of squares backwards. Now that's my common denominator, because both denominators would come out the same this way. But on top, I need to do 1 times secant of x plus 1. And for the other fraction, I have 1 times secant of x minus 1. And it was a plus in between the fractions, so make sure you don't forget that sign in there. Now we need to go back through our list of strategies. You might notice that on top, we actually have some terms that would cancel out because I have a plus 1 and a minus 1. So if those cancel, and secant of x plus secant of x, those are like terms, you can write that as 2 times secant of x. So that's just combining like terms on top. On the bottom, we see a trig expression to the second power. We have secant squared minus 1. Whenever you see a trig function to the second power, especially if there's a plus or minus 1, take a look at your Pythagorean identities, because this does have one we can use. I'm going to write tangent squared down here instead. Now this next step is going to be kind of tricky, but remember that we know we're working towards a 2 times a cotangent times a cosecant. So keep looking at what you have in your expression and see if you recognize part of it that you can kind of lock into place or set aside and stop manipulating, and then you can just focus on the rest of the problem. We have a 2 being multiplied by our expression, so I can set that off to the side. I also see that I have a secant over a tangent squared. And if I kind of break this down as 1 over tangent of x, and a separate fraction being multiplied, so the parts I haven't used yet are secant over tangent, this actually creates another one of my pieces because the reciprocal of tangent is cotangent. Now the only reason I thought to break this problem down like this as 2 times 1 over tangent times secant over tangent is because I'm looking at what I have on the other side, so I knew that the 2 times cotangent part would be useful. So this piece of the problem, I'm just going to lock into place and stop messing with. But I still have the rest of the problem over here. So now I can just think about what strategies I can apply on secant over tangent. And one of our options is to replace things with sines and cosines. So I can think of this as the fraction of 1 over cosine. That's my numerator. And we're dividing that by sine over cosine, because that's what tangent equals. but I'm going to use keep change flip on this. So instead of dividing by sine over cosine, I'm going to multiply by cosine over sine. So instead of dividing by a number, you can multiply by the reciprocal. A lot of you guys learned that as keep change flip. And the reason this was useful is because that makes the cosines from these two products cancel out. And so since I've run out of space, I'm going to carry this over here. So now I have 2 times cotangent. And instead of writing 1 over sine, since the other part's canceled, we know that the reciprocal of sine is equal to cosecant. So this was a tough problem, but use the information on the other hand, on the other side of the formula to keep guiding what your next steps should be. You just want to think about the math operations that are available to you, like factoring and simplifying, combining like terms, and try to find ways to creatively group some of the expressions together to your advantage. So that's all for the notes on how to prove an identity.